Hello everyone, my name is Belma and I'm going to present our paper, Elastic Slicing in Programmable Networks. So let's first start with introducing the concept of network slicing. So network slicing enables network operators to provision multiple virtual networks, each tailored to different service needs on top of a shared physical infrastructure. So for example, if you would have a physical infrastructure like this, with network slicing we can create virtual networks on top. For example, we can create a network like this, and as we can see, this virtual network will now consist of virtual nodes and virtual links, and each of these virtual nodes will represent a network function. So basically, it would provide a specific network functionality, and these network functions can either be stateful or stateless. So if you have a stateful NF, then the packet processing will depend on both the packet itself as well as NF's current internal state. And what is important here is that that internal state can actually change with each process packet. So for example, a stateful firewall. However, in contrast, in case of a stateless NF, packet processing will only depend on the packet itself. So in this paper, we are mostly concerned with stateful NFs, since they're more interesting and they're more difficult to support compared to the stateless NFs. And realistically, every solution that would support stateful NFs would also be able to support stateless NFs. So the second part of these virtual networks are virtual links, and these links are basically links connecting these network functions, so basically the virtual nodes. So let's now see how this would translate to the physical infrastructure. So in essence, each of these virtual nodes will be assigned to one of the physical nodes, as we can see here. And each virtual link would represent a path that can be a multi-hop with reserved network resources, so for example bandwidth, in the physical networks, so something like this. So if you would now want to create a second slice, so the green slice, we would do the same thing. So nodes would be allocated and virtual links would be reserved. And what's important to notice is that several virtual nodes can run on top of the same physical node, and several virtual links can also be part of the same physical link, as we can see in this figure. So basically the blue-green links and blue-green nodes. So in addition to this, we want to support elasticity. So I'm going to explain this in a bit more details. So traffic volumes are generally unpredictable and they change over time. So for example, the number of users being processed by a certain slice, so basically this virtual network, can change, or the volume of the existing flows that are being processed can actually change. So for example, due to the changes in the dynamics of the end user flow. However, due to this, if we would statically allocate these slices and deploy them, we would either over-provision the resources assigned to the slice, or we would not be able to guarantee a certain quality of service. Hence, we actually consider elasticity. So basically, network slicing that supports elasticity. So the ability to automatically scale the assigned network resources to match the current traffic demands. So now if the new flows would actually join the slice, our solution would simply scale the resources assigned to the slice up or down in case the flows actually leave the slice, so complete. So for example, if you look at an example, if you have this physical network with this provisioned network slice with some virtual nodes and virtual links connecting them, and let's say that we have a slice that's now provisioned to meet the demand of 2 gigabits per second. And let's now assume that at some point a new flow joins, or that the volume of the existing one increases, and this slice is no longer able to process this traffic without degradation. So to satisfy these new traffic demands, all the virtual links would need to be scaled up. So all these links. Now, if we can simply increase the values assigned to each physical link, so basically all these links, we would have virtual scaling. So basically to vertical scaling. So basically to vertically scale, we would simply increase the virtual link values. So from here, from 2 to 5. And at the same, by doing so, we would also scale up all the assigned physical links. So basically also from 2 to 5. So basically this is an example of vertical scaling. However, if now the traffic demands would rise even further, so for example from 5 to 7, we would need to scale again. So we would do the same as before. We first try to increase the first link, but let's assume that the second link, so between NF2 and NF3, cannot be scaled up, meaning that there are not enough resources on the physical links connecting these two virtual nodes. So basically, for example, this link, because for example, this link cannot have enough, it can be that this link just doesn't have enough resources. So basically, it can only support 5 gigabits per second because other resources are assigned to other slices, or the link is just smaller than the other ones. So in this case, we need to perform the second type of scaling, so the horizontal scaling. So in case of a horizontal scaling, we would create a new instance NF3 prime, and we would create two virtual links connecting this NF to NF, so basically NF3 to the NF3 prime to the rest of the slice. So to provision this in the physical infrastructure, we would first deploy the virtual node, and then we would actually create the virtual links connecting this node. So we first increase the first link because this is link between NF1 and NF2, and this link can be scaled up. Next, we would connect our new virtual nodes on F3 prime to the rest of the slice, and this can look something like this. So for example, we increase this link to 7 gigabits, and then we actually create a new link, this new link of 2 gigabits per second, connecting this NF3 prime to the rest of the slice, and finally we also increase this last link. So now all the between so basically this slice can now support up to 7 gigabits per second because the traffic is split between NF3 and NF3 prime. NF3 prime is processing 2, while NF3 is processing 5 gigabits per second. So in this paper, we consider both of these types of scaling, so both vertical and horizontal. However, since horizontal is more complex, I'm going to focus more on horizontal scaling in this presentation. So the main difficulty with horizontal scaling comes with dealing with state and stateful NFs, as I explained before. So for stateful NFs, the processing depends on the current of the internal state of the NF. So basically, if we would reroute part of the traffic to be processed by NF3 prime, we would also need to make sure that the state belonging to that flow is correctly transferred from NF3 to NF3 prime. So basically, when the first packets belonging to these flows arrive at NF3 prime, they will be processed using the correct state information. So in addition to this, we consider all this in the context of the P4 programmable data planes. And the main reason for this is that by being offloaded to P4 programmable switches, NFs can actually benefit from hardware accelerations, which could increase their performance, obviously. However, at the same time, programmable hardware can actually process packets at terabyte speeds. And while processing each of these packets, the state of the NFs can actually change, and hence these changes can be very frequent. Just any controller-driven scaling that would simply read the register state of basically one NF and deploy to the newly created NF in case of horizontal scaling would not be able to do so on time. So basically the state would already be outdated or updated by the other packets being received by that old NF until the controller is actually able to reroute the traffic and deploy the state. In addition to this, programmable data planes enable new monitoring features that enable the data plane to report the exact QoS state the packets experience while being processed. And we want to leverage this to basically want to use these advanced monitoring features to detect when scaling is needed, and we don't want to depend on our controller to do so. Hence, the main goal of this paper was to actually develop an elastic slicing framework for P4 programmable network devices that would satisfy the following requirements. So it would economize on the slice resource utilization, it would maintain state consistency, and it would have a low scaling time. So I'm first going to explain the main components of our framework, and then I will go into some more details of each of them. So we proposed a hierarchical framework that consists of two main components. So the first of these components is a central controller. So the central controller has a global overview of the network, as well as all the available network resources and the existing traffic flows. So in our framework, the central controller will determine the network's long-term behavior. So it's, for example, responsible for initializing new slices, finding the most appropriate locations to place NFs during scaling, and guiding the second component of our framework, so the data plane component. So the second component is run inside the virtual node itself, hence it in parallel to the other NFs, so basically to the network functions, so the virtual nodes that I mentioned before. And basically this component is using the central controller's input, as well as the measured traffic conditions to perform all the latency sensitive tasks. So in this case, it's responsible for load monitoring, state management, and flow rerouting. So basically these three functions form our data DPC component. And in addition to this, to support the exchange of information between these different DPCs, so basically because each DPC would be run at a different virtual node, we created an additional protocol, our own slice management protocol that has these fields, and I'm going to explain how this is used in a more details a bit further along in the presentation. So now let's see how these components of the framework would actually interact with each other during scaling. And in here I'm going to focus on scaling out, but other examples, other information about the other types of scaling can be found in the paper. So for example, let's assume that we have a network that has a slice that's deployed with these virtual nodes and these virtual links. And as basically in any SDN scenario, these would be connected to a central controller that runs the previously mentioned components. However, in addition to this, each virtual node will run the DPC component as well, as we can see here. So DPCs would continuously track the slices utilizations using their load monitoring module. So if they would detect overload, they would inform the controller. The controller subsequently determines the switch where the new NF will be deployed on, and the route to connect that newly deployed NF to the rest of the slice. So for example, the CC then deploys the NF to, let's say, this node, and now that node also becomes virtual node and will run its own DPC component. So what now remains to be done is to create a virtual link. Run its own DPC component. So finally, the central controller also informs NF1, basically the first NF, to divert a portion of its traffic to the newly deployed NF. So basically, as I mentioned before, to not have a degradation of the flows that are being processed by the slice, part of them usually needs to be diverted. And what now basically remains to be done is actually to create a virtual link and connect this newly deployed NF to the rest of the slice. And of course, what we need to do is, because this NF is now a copy of the other NF, we also need to transfer the state that belongs to these flows that would be diverted to the newly deployed NF. And this is done in the last step, so step 6, which is basically route transfer and to creation of the new virtual link. And in this case, at the end, this would the other part of the slice would actually now process part of the traffic. So due to the time constraints, I will only go into the details of the scaling out for the steps 1. So basically the load monitoring, and the last steps was sticks. So reroute virtual link creation and state transfer. However, you can find more information in our paper about all the other steps. So let's first see the load monitoring, so step 1. So if you, for example, have a network that would look like, for example, this, and let's say that it has these 3 virtual nodes, and the first value under these links represent the reserved amount of resources to this slice, and the second one represents the amount of resources still available on the link, so the amount of resources we can still assign to the slice. So basically, to determine when scaling is needed, we deployed a set of meters on each of these virtual nodes. And we used a set of registers together with these meters to monitor a set of stats. So for example, for scaling out, these would be the growth rate and the growth counter, so RG and CG in this figure. So the growth rate, RG, tracks the number of yellow packets processed in the last interval, while the growth counter uses the growth rate, so RG, to track the overall trend of slice utilization. And it's basically calculated. So if the number of yellow packets, so the growth rate would increase between two subsequent intervals, CG would also be increased by 1. However, if it would remain the same or if it would reduce, we would reset it to 0. In addition, if there's a red packet, so basically, in addition, if the growth rate increases or the number of red packets is not equal to 0, we would increase CG. So this way, if the slice utilization would continuously increase for at least some m intervals, scaling will occur. So there's basically a threshold that says after this many intervals, I'm assuming that the slice utilization is continuously increasing and the new NF should be deployed. Well, okay, scaling will be initiated, so it can also be vertical scaling or horizontal scaling. So let's assume here that first vertical scaling was performed and then a new virtual node was actually created. And now this new virtual node, so NF2 prime, will also run the load monitoring. And as we can see here, in contrast, if there is not a continuous increase in utilization, so if there are like small fluctuations, our DPC component, so the load monitoring component, will actually filter this out. So we can see here that the CG actually increased, but then because the slice utilization actually went down, no scaling was actually initiated. So I'm going to move on to the second component, which is virtual link configuration and state management. So this is step 6 from that I mentioned before. So after the NF is deployed, how to reroute the traffic and transfer the state. So if you look at basically again an example network with these NFs, so these virtual nodes. Let's say that we want to transfer the state from NF2 to NF2 prime. And this state is actually stored in a register of on NF2. And let's say now that the central controller decided that the flow that we would reroute, so the flow to divert, is flow B. So to support this, we first added a bit array that we see here that will indicate if the state was transferred or not. So basically, if the state of this flow should be on NF2 or NF2 prime. And now, when NF1 receives a flow belonging to flow B, it would first forward it to NF2, but add an additional SM header. So basically, the state management header that I mentioned before, so our custom header, and basically it sends a pickup packet to NF2 to basically pick up the state. And we can see that this now packet will have the following headers. So basically it has certain type, we indicate which flow we want to divert. This was calculated by the central controller. And as we can see, the state is not yet known. However, when this NF2 actually receives this, it will create a copy, update its SM header, so process the original packet further along the path, create a copy, and populate the copy with the state information and send it back to NF1. And in addition to this, it would set the bit register to 1 to indicate that this flow is now transferred to NF2 prime. And now this NF2 knows that this B state was migrated. So if the new packets would be received by NF2, we would know to actually send an update to NF2 prime. And it will now send back this packet, so basically clone packet back to NF1. NF1, while processing this packet, so basically this packet now contains the state information, and NF1 will now change this SM header, update its own forwarding rule, as well as the resources of its output link, so adjust this value, the allocated bandwidth, and update the SM header and send it to NF2 prime. So basically now this SM header will contain the other route, so that have the other type and contain the other length and route. So basically this is a source route from NF1 to NF2, and basically we'll have the state information. So now NF1 actually has the forwarding rule to forward the packets belonging to B to NF2 prime. This switch will also repeat the same process, so it would update its forwarding rule, and it will actually update the SM header, so the source route, it removes one of the ports, and it will allocate the resources on its output link, as we can see here, and forward this packet again to the NF2 prime. And upon reception, NF2 prime, whose state table is now empty, because this is the newly created NF, will actually populate it with the information, so basically state information, and update its state. So now we can see that both NF2 and NF2 prime have the state information. In addition to this, the flow was effectively rerouted on NF1, and the new forwarding rules were installed. Using the same procedure, the link from NF2 prime to the next NF in this would be also created. And in addition, we see this one. So basically, if a packet belonging to flow B is received by NF2, NF2 will send an update to NF2 prime. This can happen because there were packets already, for example, on the link between NF1 and NF2 that belong to this flow before the flow updating, the rerouting rule was actually changed. So I'm now going to go through some of the most important results we had. So additional results are actually available in the paper, and I'm only going to go through some of the most important ones. So we tested our solution with both the Tofino switch and in Mininet, and we deployed the NF. For the NF, we chose the counting NF since it's the one that changes the state most often. So first, if we compare the controller-driven approach to our approach, so data plane approach, we can see that the controller-driven approach was not able to maintain the state consistency. So usually the poll data was already outdated after it was deployed in the new NF. Hence the state the controller deployed was no longer relevant, and more importantly, the controller was never actually able to recover from this. In contrast, the data plane approaches were able to maintain state consistency. Also, if you look at the overhead during scaling, we can see that the rerouting in the data plane significantly reduces this, and the controller was usually the bottleneck in our scenario. So basically removing the controller actually helps significantly. And finally, due to the more accurate overload detection, scaling was initiated earlier and improved the performance for the end users overall. So finally, to conclude, in this paper, I presented a elastic slicing framework targeting P4NFs that actually offloads time-sensitive tasks to the data plane. And we have shown that by having an intelligent data plane, on-time scaling can be realized and performance can be improved significantly. Thank you.